like most people are getting signed on. While the last few people join us, I just wanted to point out really quick, I started a discussion for us that has some of my troubleshooting guide for Segal, and then also as people send me more errors they're getting, I will try to add little posts with hints at how I solved those errors as we go through. So I've got a few that I've been able to add since I made that first troubleshooting document. So hopefully this will be somewhere, if you guys, it should be open that you can submit solutions you find too, if you are comfortable doing that. Or if you want to submit a problem and see if other folks have had it or if I have seen it before. Or you can just email me and I will try to answer it. So I just wanted to point that out. The other thing, I'm gonna send out an announcement about this as well, but next Tuesday we have our guest speaker. So for people who have been attending asynchronously or participating asynchronously, obviously that's been fine. I am totally cool with you doing that. But on Tuesday, I think this would be the one day where I'm going to highly encourage you to come in person and join us during that time, since our guest speaker will only be here for one day. So if you want to ask her questions and learn about AGN research, it'll be good for you to actually be in class that day. So this will be the only day where I really push for everyone to come, especially because she is volunteering her time. I am not paying. So I think if we can show her appreciation by actually being here that day, that'll be great, or next Tuesday. So Tuesday the 27th, I'll send out an announcement reminding y'all, but this will be the one day where you will be able to earn points asynchronously still, but I'm going to highly encourage you to attend in person. Any questions on anything so far before we get started? Cool. So today we're gonna start kind of moving out of our discussion of spectra just really and start talking about some galaxy evolution. There's one more day, because we moved some things around, there's one more day that'll be kind of talking about spectra next week, but then it'll be more, what are the galaxies in our local universe? What's the large scale structure? Trying to put some of what we've talked about together to think about how we can use the skills we've developed to actually study galaxies and the evolution of our universe, which is fun and is kind of the overall goal of extragalactic astronomy. So to kind of start that, we're going to start by talking about galaxy collisions, because they're fun and awesome and just also very important parts of how galaxies change and evolve. So like I said, we should study, why should we study galaxy collisions? First of all, because they're cool, because they produce really beautiful structures, but also they're just a big part of how galaxies change, how galaxies evolve. So by studying galaxy collisions, we can understand a lot about galaxy structure, galaxies, why galaxies look the way they do, and how that has been changing throughout cosmic time. So very important to study these if we want to understand galaxy evolution. Merging galaxies, interacting galaxies will also change element abundance. So it will change the metallicities we measure by just dumping a lot of gas between two galaxies, exchanging gas. And then they also, how galaxies collide and what happens after a galaxy collides has some implications for why we see elliptical and spiral galaxies and where we see elliptical and spiral galaxies in our universe. The last little thing, nugget as to why we should study galaxy collisions is that they provide a unique laboratory for studying how dark matter halos will interact. So usually you have a dark matter halo by itself with one galaxy. When you slam two galaxies together, you merge those two dark matter halos as well as the actual gas and dust and baryons in the galaxy. So by looking at the mass distribution in merging galaxies, we can get an idea of how dark matter interacts with itself. So how dark matter particles interact with other dark matter particles. The thing to point out first when we think about how we observe galaxy collisions is that we can't watch two galaxies merge together. That is not something we have had telescopes around long enough to do because these processes happen over extremely long periods. So it takes around 3 times 10 to the 8th, so 300 million years for two galaxies to kind of finally merge together. So what we're seeing instead of actually two galaxies merging is snapshots of many galaxies merging and comparing those. So comparing galaxy A and B over here that are merging to galaxy 1 and 2 over there that are also merging to see what merging processes look like at different times, with different galaxies, and build a picture of how merging affects galaxy evolution. We can, of course, the good news is, sorry, stepping through my bullet points. The good news is merging galaxies are incredibly bright at a wide range of wavelengths, so they're pretty easy to observe. So despite the fact that we can't watch one galaxy merge, we can see a lot of galaxies in the process of merging because they're just very, very, very bright as they go through these processes. So as a little example, two galaxies colliding will have a collisional energy of about 10 to the 53rd joules, which is similar to 10 to the 8th supernova going off. So very, very, very bright. And then will be occurring for a fairly long time. So if we think about a luminosity is an energy per time, so we take our collisional energy, we divide it by our time for a collision to happen, and we get luminosities of 3.2 times 10 to the 37 watts, or 3.2 times 10 to the 44 ergs per second. So just very bright objects in our universe, things that we can observe pretty easily, despite the fact we can't watch one happening throughout an entire process. We can also, I will talk about this more at the end, but we can also use models of galaxies to smash two galaxies together in a computer simulation and see what that looks like. And that's how we learn a lot about what we expect to see in galaxy collisions. The last thing we can do is, instead of observing two galaxies colliding, we can look at tidal streams around galaxies to get an idea of how merging events have happened in the past. So just in a reminder, with the Milky Way, we've been able, with Gaia and other detailed measurements of the stars moving around the Milky Way, we see things like the Sagittarius stream, which is shown here, that shows the motion of what was the Sagittarius dwarf galaxy that got eaten by the Milky Way. So we can look at these tidal streams and get an idea of the merging history of the Milky Way galaxy, as well as other galaxies that are near enough we can actually observe these tidal streams. The next thing to think about is that when we talk about galaxy collisions, galaxies aren't like frisbees. They're not solid disks of material. They're kind of dispersed gas, stars, dust inside of a dark matter halo. So when we say galaxy collisions, it's a little weird to think about what actually is colliding. It's like two things merging together. But for the most part, the stars in a galaxy are spread out enough that no star is going to run into another star. So for example, like I love doing outreach, and I love telling people that Andromeda and the Milky Way are going to merge together. And their first thought is like, oh no, another star is going to hit the Earth. And it's like, nope, not going to happen. That is not what we need to be worried about. That is not an issue at all. The stars in two galaxies, when they collide, will for the most part just pass right by. And eventually, as the two galaxies make a few passes and settle down, it'll perturb their orbits around the center of the galaxy. It'll change how they move around the center of the galaxy, but there won't be any star-star. There will be maybe a few, but very, very limited star-star collisions. Despite the stars being pretty spread apart, the gas in a galaxy disk is spread pretty much throughout the disk, so you actually do kind of have a disk of gas. So when you slam two galaxies together, what really is colliding are the gas particles in these galaxies. So that's what a lot we see is the gas actually hitting each other. As the gas collides with the gas from another galaxy, it'll get excited, it'll heat up, and we can observe it in the X-ray. We'll also get spikes in star formation as gas clumps slam together and get to the density conditions necessary for gravitational collapse to occur. The other thing that kind of collides, although this is a little weird, is the dark matter halos. So the dark matter is another thing that seems to be spread fairly uniformly throughout the halo. There's that kind of core cusp model where maybe there's more dark matter in the core of the galaxy, maybe there's less dark matter in the core, but however you look at it, it's pretty well distributed throughout the whole halo of the galaxy. It's not like stars where there's discrete packets of dark matter. It's just all kind of there. So when we slam two galaxies together, we are actually merging their dark matter halos. So there's just a lot of opportunities for dark matter to interact with other dark matter in this process. And this is where we get kind of our second key observation that dark matter must be a thing, is by looking at colliding galaxies and seeing that the distribution of mass does not match the distribution of either gas or stars. It is usually between them. So that gives us an idea of how dark matter interacts with itself. And that's what this image, whichever way it is showing. This is the bullet cluster as taken by the Chandra X-ray Observatory, sorry. And so we're seeing the gas is what we're seeing in the actual light, these bright spots here and here show where the gas is colliding, the two gas disks are colliding, and we're seeing higher energies as those gas disks interact. And what the contours are showing is where the mass is distributed in the bullet cluster. So we can see that the mass of the bullet cluster does not match where the gas is. We can't really see it in these images, but if you could see, the stars would be outside of this. So the stars go right through, the stars pass through, so the stars would be further out. The gas interacts strongly, so it actually hits each other and slows down, and it starts to collide and heat up. The dark matter, where most of the mass is, interacts less than the gas, but more than the stars. So it ends up passing through each other and slowing down slightly as it passes through, and the distribution of the mass doesn't match either the distribution of the gas or the distribution of the stars. So this gives us some idea of how strongly dark matter interacts with itself, because it tells us how much the dark matter halos got slowed as they passed through each other. So this is kind of when we talk about galaxies and how we can use galaxies to study dark matter. The two main ways we can do that is by looking at the rotation curves of galaxies and also by looking at colliding galaxies and mapping where the mass is in those colliding systems. There are other ways that we have evidence for dark matter, but those more fall in the cosmology bin, so I'm not going to get into them in this course. The last thing I want to point out in this image, the way they measure where the mass is by looking at how the light from distant galaxies is distorted around the bullet cluster or the bullet cluster collision. So we can measure where the mass is by looking at how light is distorted and bent as it travels through the bullet cluster. So another way we can measure mass, but again, is kind of more cosmology than galaxies. But I thought I should mention it because otherwise it's hard to imagine how we can get an idea of where the mass is just by looking at this image. Any question about anything so far?
I just have a quick little fun fact about the bullet cluster. The way that they know that the mass distribution is dislodged from both gas and stars is because of microlensing. So that's how we observe dark matter, which is cool.
Yeah. So that's that light traveling through the curved space-time. Yeah, it's very slightly more cosmology. No, sorry, yeah. Cool. So now we're going to get a little bit more into how we can classify collisions. So the first kind of big ways we can break up collisions is by thinking of them as either tidal interactions versus true collisions. So a tidal interaction will be when two galaxies pass close enough by each other that the gravitational forces between the two galaxies will distort the disks or the shapes of the galaxies without actually having the two galaxies merge. So this might be kind of an image showing a tidal interaction where the two galaxies haven't actually crashed into each other, but we're seeing that the gravitational pull of this larger galaxy is changing the structure of this smaller one down here. A collision then is when the two galaxies actually pass through each other, which maybe the system, ARP273, will eventually go through a collision process, but at this point it is not. The other way, the kind of big category we can break collisions into are minor mergers versus major mergers. A minor merger is when one of the galaxies is much smaller than the other, so about 10% the mass of the other. So if one galaxy has 10% the mass of the larger galaxy, that would be a minor merger. So for example, right now the Milky Way is slowly eating the large and small Magellanic Clouds, and those would be examples of minor merging processes just because the large and small Magellanic Clouds are so much smaller than the Milky Way. Major mergers are then when the two galaxies have similar masses, so them slamming together will have just a greater effect on the galactic environment inside both. So those are very broad categories. I'm now going to get into a little bit more specifics on different morphological categories of galaxy collisions. So these are kind of similar to how we think about how we classify galaxies using the Hubble tuning fork. We can do the same thing with colliding galaxies. We can break them up into different morphological classes, and their morphological class will tell us a little bit about what we might expect for the two galaxies to do in the future as they continue merging and colliding. So we classify merging galaxies with four main parameters. The first is going to be the types of galaxies involved. So do you have two ellipticals, two disk galaxies, or an irregular galaxy, or do you have one elliptical and one disk galaxy? So that's going to be your first parameter. Your second parameter, and this one's a bit harder to tell, so all of these are slightly fuzzy, just like, the difference between SB and SC is kind of fuzzy. The difference between some of these is also a little fuzzy. So the second parameter is the time since the collision began. So you can have a young collision, a young merging process, where maybe they're just starting to get close to each other, just starting to merge. You can have an intermediate collision process where they're in the process of merging. Maybe they're going through, they're starting to settle into just one galaxy. Or you can have an old merging process that has happened a long time ago and we're getting close to, instead of two galaxies smushing together, just kind of one larger galaxy that is the combination of the two of them. The next thing we can think about is the relative masses of the two galaxies. So this is kind of similar to that minor merger versus major merger, just now giving it a little bit more of a parameter space. So a small morphological, so a minor merger kind of thing, where one of the galaxy is 10% the mass of the larger. Medium, where the smaller galaxy is 10 to 50% the mass of the larger. And then a large collision where the smaller galaxy is 50% or greater the mass of the larger galaxy. Okay. So that's going to be our major mergers in the last category. The last thing that we can think about is how the orbits of the two galaxies relate to each other. So are they orbiting, if we have two disks, this is only really going to matter, it's going to matter most if we have two disk galaxies, which usually is the case, not always, but often is the case. So if you have two disk galaxies, are they rotating in the same direction? Are they prograde slamming together? Are they rotating in a more orthogonal way, where we have one oh my gosh, one going like this and one going like this. This is like rubbing your head and patting your belly, whichever way. And then, or the orthogonal, wherever they're rotating in the opposite directions. So for example, this pair of colliding galaxies, I'm going to do one, then you all will do one. So this pair of colliding galaxies here, we can see they're both disk galaxies, and they're both, and they look to be fairly similar in mass. So if we could actually get a mass, we could get better, but they look to be fairly similar. So I'm going to say this is a large. So that means we have capital D, capital D. So if one of them was small, I would do a lowercase d to represent one of them was small in this small category. I'm going to say that this is an intermediate range. This is, again, it's either young or intermediate because you can still really see that there are two distinct galaxies. So I'm going to call this intermediate. So I'm going to put an I there. And then we can see that they're rotating at a 90-degree angle from each other. So they're going to be an orthogonal rotating system. So that should be a 0. Kind of looks like a 0. Maybe it looks like a ghost. I'm trying. Okay, so we have our classification for this system is that it's an intermediate merger with two large disk galaxies that are rotating in an orthogonal manner. So that's kind of how we go about classifying. Now, I'll leave that up so you can remember what it looks like. I want you all to do your best to classify the Whirlpool galaxy, I think. And when you have your idea of what you think it is, you can put it in the chat. Some of the parameters are more visually obvious than others, but do your best. Seen one answer. You can get a few more. I wonder if I could have made this as a poll. How many? I would have had to make like a bunch of different. 4 to the something. Yeah, so I've got a few answers now that look kind of similar. Some of you agree with me, some of you have a slightly different idea. I said that this was going to be a young, so why? Some of you said intermediate, also fine. Like I said, the boundary between those is kind of fuzzy and hard to tell, but I thought this was young because we can still really see two distinct disks. Again, hard to tell the actual boundary. One large disk and then one smaller disk. So I said capital D, lowercase d. And then it looks like, to me, again, this is kind of hard to tell because we don't actually have rotational information for these two galaxies. But to me, it kind of looked like they were probably rotating in opposite directions from each other. So I said that it was going to be a negative retrograde. So that would be how I would classify this. Again, whether you choose Y or I for this classification and what you put here, it's a little hard to tell just based on the information you have, but like I said, kind of doing our best with just an image. Any questions about why I chose what I chose? And so the cool thing is, just like knowing if a galaxy was an elliptical or a spiral gave us some idea of what's happening or what might happen in a galaxy. Knowing the morphological class of a collision might tell us a little bit about what we think eventually is going to happen as these two galaxies merge. For example, if one of them is a lot smaller, we can use the fact that we know that smaller galaxies have been merging into the Milky Way throughout cosmic history, and that hasn't changed the Milky Way. It hasn't made the Milky Way not a disk. So we're still a disk galaxy, despite the fact minor mergers have been occurring. So we know that, so we can say that if it's one of them's much smaller, maybe we end up with a disk. We can also use some observations of where ellipticals are and just models of what happens when you slam two galaxies together orthogonally, to say that when you take two rotating disks and you slam them together orthogonally, their velocities get really perturbed, and what you end up with usually is an elliptical galaxy. So that's one of the keys, that like maybe the way we get ellipticals is through orthogonal or closer to orthogonal collisions of two large galaxies. So this galaxy in my previous slide, these two systems might eventually end up becoming a giant elliptical galaxy as they merge together and their orbits get so perturbed, and they end up just, instead of having nice rotation, just having a lot of random motion because we slammed two orthogonal disks together.
Oh, I actually have a question. Is there any symbol in like the shorthand classification for like like saying whether their masses are different? Or because I know like the disk and like the young intermediate thing and then the orbit, but then that's my question.
So I guess, so that has to do with whether you do a capital letter or a lowercase letter.
Oh,
So that would be, so the medium, I'm not really sure exactly what you would say, but if they're both large, then you do both capital Ds. If one of them's large and one of them's small, you would do a lowercase letter. So that was why with this one, I said that there was a large D, lowercase d. So we have a large disk and a small disk.
oh, okay. Thanks.
Another thing that you might, so this is kind of breaking from that, another thing we can think about is that even if the galaxies don't collide, or even with minor mergers, you might end up with some perturbations of your disk. So looking at this galaxy here, things happened, like potentially even we can see there's a lot of light going on in the halo. Maybe this was like a medium-sized galaxy that collided with this disk galaxy, and maybe it was slightly closer to prograde or retrograde, and so we didn't get as much disruption in the disk, but we still got some bending and flexing. So even if you don't completely destroy your disk in your galaxy collision, you can really change the kinematic properties of a galaxy when you slam two galaxies together, which maybe isn't super surprising. This is also how we think back when we were talking about rotation. I showed you a galaxy that had a counter-rotating gas disk, and the idea is that that probably happened with a galaxy collision. So maybe that was two disk galaxies, but one of them was rotating retrograde, and somehow that just, when they add in the process of merging, the gas continued rotating retrograde while the stars ended up going prograde, some craziness. But so you can get, besides actually just destroying nice rotation altogether, you can get weird perturbations like this curved disk in galaxy collisions. You can also get cool things like ring galaxies. So if you have a young disk, large disk, small elliptical, orthogonal rotation, although if it's an elliptical orthogonal, everything's orthogonal because only one of them has rotation. So that's a little weird to say, but if you have a galaxy of this morphological class, you can get these really pretty ring galaxies where there's, we can kind of see the remnant of the small elliptical that's being merged together with it. And in this merging process, there's going to be a spike in star formation around a ring in this galaxy as gases merge together, and shocks happen, and we get the density properties where gravitational collapse will occur, and we get star formation happening in this ring. So another way that we can use morphological classes to kind of get an idea of what we might expect two merging galaxies to eventually become, or even if they are not at that stage quite yet. And it's just a pretty thing that we see in the universe. And part of galactic astronomy should be looking at pretty pictures of galaxies because galaxies are beautiful. Another thing that happens in this whole merging process, and one of the most important things, is that galaxies will exchange materials as they merge, specifically gas and some dust. And as they exchange gas and dust, you're changing the chemical compositions of the two galaxies. So you might be enriching one galaxy, or can't think of the opposite word of enriching is, sorry, losing material from one galaxy. But this will also fuel bursts in star formation. When we give one galaxy a lot more gas, all of a sudden there is more stuff to form stars. So we see one of the reasons why merging galaxies is so bright is because they are often going through incredible bursts in star formation. Merging processes might also fuel AGNs as well as star formation. This is a little hard to classify observationally, so some of this is based on what models say should happen, but it's harder to do just because there aren't very many nearby AGN galaxies. So it's hard to tell how important collisions are in fueling AGNs because we don't have as many nice observations of AGNs where we can tell whether or not they're colliding galaxies. But these collision processes do send a lot of new gas into galaxies, mixes up the gas in these two galaxies. So some of that gas could be fueled onto the supermassive black holes and potentially spark an AGN. So AGNs are where we have a lot of accretion of gas onto the central supermassive black hole in a galaxy. And as that gas falls into the black hole, it moves very quickly and we see bright X-ray sources, these quasars or AGN, depending on what you want to call them. There's also a possibility, maybe we don't really completely understand this, it's kind of hard to observe, but it's possible that when we slam two galaxies together, their supermassive black holes could become a binary system that could eventually decay in its orbit and become one even more massive supermassive black hole. So kind of hard to observe. Some models show this happening eventually, but on very long time scales. It's going to take a really long time for the orbits of this binary supermassive black hole to decay enough for them to merge together. Some simulations show one black hole getting kicked out of the system altogether. So you merge your two galaxies together and one of them just flies off. Again, kind of hard to observe because how do you observe a black hole if it's just flying through space? It's hard. It's likely that merging galaxies might spark AGNs or at least fuel an AGN for a short period, but it's difficult to quantify exactly how frequently this happens or if this is the main reason why we see AGN. Another cool thing is that merging galaxies, we're pretty sure, drive galaxy evolution for multiple reasons. So this is one of my favorite things to think about. I just think it's really cool. And it was also my first research experience I did in REU, where we were looking at galaxies at a redshift of 2 and trying to see how many of them were merging. So I always get excited about this. But the main point is that when we look at something called the cosmic star formation rate history, which is what this graph is showing. So the cosmic star formation rate history is where we plot time or redshift. So look back time, 0 being now, redshift of 8-ish is approximately the Big Bang. So you can't really form galaxies earlier than this for the most part. So look back time or redshift on our x-axis. And then our y-axis is this parameter phi, which is star formation density. So it's the star formation rate, solar masses per year, and then per megaparsec cubed. So it's the star formation inside a 1 megaparsec volume. So it's giving us an idea of kind of a average star formation rate in the universe over time. And what we can see is that there's this really interesting spike or peak around a redshift of 2. So about 10 billion years ago, galaxies were forming stars more efficiently or just faster than at any other point in universal history. And understanding why that occurs is a big part of how we can understand why we see the universe we see today. So it's a really cool graph. There's a lot of information in it. The other thing to point out is these data points are very, very, very uncertain. So do we know if it's really this steep of a bend? No, we don't. I don't know how they got these error bars. I disagree with them. I think they are wrong. I've read this paper. It's a great paper. I disagree with these error bars. Make a lot more sense to me than these ones do, because we cannot measure star formation rates for the most distant galaxies very well. We don't have a good way of doing that right now. But what we do see is that when we look at galaxies at a redshift of 2, there also seem to be a lot of galaxies that appear to be merging at this time. So that's what I'm trying to show here. These are really fuzzy images because we only have fuzzy images of high redshift galaxies. But what we can see is that at a redshift of around 1-ish, things are starting to look like disks. We're starting to see things that look like disks. But as we get closer to 2, we see more and more systems where we can see kind of multiple nuclei that seem to be slamming together. So at this redshift of 2.1, it looks like there's maybe 3 galaxies that are in the process of merging. This 1.3, maybe there's 2. Down here at 2.7, it looks like there's 2 things that are pretty close to merging. At 2.8, maybe there's 3 in this image. So by using things like the Hubble Ultra Deep Field and other surveys of optical surveys of really distant galaxies, we can see that at the same time that there's this spike in the cosmic star formation rate history, there also seems to be a large number of colliding galaxies. So it seems like this peak is probably due to galaxies colliding, leading to a burst in star formation that then falls as we start to run out of material to form new stars. And the galaxies that went through this burst are becoming red and dead ellipticals, and the galaxies that didn't are still slowly chugging away, forming stars, but at a much slower rate. So I just think that's cool. And it's fun to think about. So the next thing I'm going to talk about is going to get a little bit more into how we model these and how we kind of build a total picture of galaxy collisions. Does anyone have any questions about any of what happens in these colliding processes that fueling star formation and AGNs and driving universal evolution? Okay. Not hearing anything, not seeing anything in the chat, but always feel free to interrupt me at any time. So the last thing we're going to discuss before I let you get into the activity for today, which is going to be more of a, not a coding thing, more a discussion thing, using what you've learned, is how we think of the different stages of collision and how that applies to galaxy evolution. So this is kind of all, you'll see the last thing I'll show is a paper, is an image from a paper by Phil Hopkins, who is one of the people who runs the FIRE simulation. So all of this is kind of built around simulations of colliding galaxies. But we can also compare those simulations to observations to see that it does kind of fit what we see in the real universe. You can tell I'm an observationalist because I don't trust simulations. But we see the same thing they're seeing in the simulations we do tend to see in actual merging galaxies, so it's good. But the first stage in a collision process is going to be single disks and then interacting galaxies. So kind of the first couple stages are single disks and interacting galaxies. So that's kind of like what we're seeing here. These would be those interacting pairs, maybe we're not quite to a collision yet. For these galaxies, star formation rates will be fairly stable. These disk galaxies, we would expect to have star formation rates of around 10 solar masses per year or so. Just kind of, like I said, chugging along, forming stars out of the gas in their own disk. During these stages, the main changes that are happening in the galaxy are driven by stars forming and dying. So any changes that you see are because we are either creating new stars or those stars are going supernova and dumping material onto the disk. And as two galaxies get closer, there will be dynamical interactions that might change the angular momentum, change the rotation rates and kinematic properties of the galaxy, which can also influence star formation rates, but while they're just kind of slowly orbiting around each other, we don't expect too much of an influence. The next main stages are coalescence and the ULIRG stage. So I think I've said ULIRG a couple times, I've thrown that term at you, but just as a reminder, and to say it again, ULIRGs are ultra-luminous infrared galaxies. You can also have just plain LIRGs, which are slightly less infrared luminous, but still very luminous in the infrared. And then there's also a class of galaxies called hyperLIRGs, so HLIRGs, which are even more luminous in the infrared. We kind of define ULIRGs as galaxies with infrared luminosities greater than 10 to the 11th solar luminosities, so very bright in the infrared. And this is kind of as the galaxies are merging together, there's a lot of mixing up of the gas, there's gas flowing into the core, and there's also a lot of dust mixing together. So the large amounts of dust mixing together mean that even though there's these huge bursts in star formation as we mix the gas together, some of that light is blocked by dust. So they're mostly luminous in the infrared. So we are merging gas, we are merging dust, we have a huge burst of star formation that's heating up the dust, which is blocking some of that UV light, some of that O and B star light, but heating up the dust, which then emits in the infrared, making these extraordinarily bright in the infrared. During this process, there will also be gas inflow onto the core, so into the center of the galaxy, which could lead to a buried AGN inside of all the dust and gas, but we won't actually see it as an AGN the way we typically think of AGN, so a little more difficult to tell if it's there. So just as an example of galaxies in this stage, this is I think it's the bird galaxy is what this one is called. But a cool thing we can see by looking in X-rays, if you look at the core of this galaxy, you can see there's three kind of large masses that we think are three supermassive black holes that are kind of from the center of potentially three galaxies that are in the process of merging here. Potentially 1, 2, 3, or maybe one of these galaxies that is merging, maybe there's only two, but maybe one of the two galaxies went through a major merger in the past and so already had two supermassive black holes. So maybe S1 and S2 are both from the same and N is from the other. We're seeing them slowly get closer together, which again, cool. The next stage is going to be the blowout and the quasar stage. So during this stage, the black hole will grow very rapidly as material from the gas and dust slowly falls onto the black hole. So this will cause, gas getting caught in the accretion disk of the black hole will also cause major jets out of the black hole as some of the material falls in, but some of it gets pushed out by just kind of the extreme winds around a black hole. And that will slowly, so that's the kind of blowout of this phase. There's also going to be a lot of supernova going off after that burst in star formation. So during this period, we're just really depleting our disk. Depleting, that's the opposite of enriching. Okay, sorry. We're depleting our disk of gas. So we're depleting our galaxy of gas either through jets from the quasar in the center or through supernova blowing material out, but we're kind of losing gas. So the star formation rate starts to really slow as we lose our material to form new stars. But during this process, there is still material that some of that supernova ejecta, some of the gas is still falling into the center black hole. So we are still seeing that quasar in this process. The last stage of all that ends this strange, eventful history, to quote Shakespeare briefly, is death and the kind of becoming an elliptical. So after you have your quasar, the quasar will rapidly fade as it runs out of material, as it accretes all the gas around it, and some of it gets blown out through jets. And we will see kind of just the remnants of all the star formation that happened, all of the craziness that happened. There will be some evidence of potential tidal interactions, where we can see how the galaxies slowly slam together and stars got mixed up, and you can see the remnants of maybe velocity structure from disks. But those will be lost as the rotation of the stars kind of gets mixed up, and you end up with a red, dead elliptical. So this here is the Atoms for Peace galaxy, just kind of a fun little story. This galaxy was given its name by President Eisenhower in 1953 because they thought it looked kind of like an atom, and they wanted people to think that nuclear power was a good thing. So they were like, look at this pretty galaxy called the Atoms for Peace galaxy that shows us that it's okay to work with nuclear power. I don't know. So that's just a fun little story about how we tried to use astronomy to do some public, I don't know, propaganda for US nuclear energy. But you can see that maybe there was a disk galaxy here in the center that's slowly being kind of consumed and turned into this larger elliptical that probably went through a very catastrophic merging process and is now settling into its red and dead elliptical stage. So to put all of this together, this is the paper from the simulations paper, so Hopkins 2008, I believe, where we can say we go isolated disk, small group with interactions, coalescence to our ULERG, the blowout and quasar phases, and then slow decay into a dead elliptical. So that's just showing all of this. The other really cool thing from this figure and why it gets thrown around a lot is this center graph here. So the x-axis for both of these graphs is time relative to the merger. So 0 is when the merger really happens, this kind of D, E, and F stage where the galaxy really is combining into one. And then on this top graph, we're seeing what we would expect star formation rate to be over time for this simulated galaxy. So we can see before they collide, we've got a pretty steady 10 solar masses per year. As we start to get some interactions, as things start to kind of merge, we get dynamical perturbations from the two galaxies. Maybe there's a brief, a little bit of an uptake in star formation rate as some of the gas gets shocked and slammed together. There's velocity perturbations. So maybe there's a little uptake, but things settle down as maybe the galaxies pass by each other the first time. And then there's a huge uptake when we hit that ULERG stage. So just a very, very bright, almost 1,000 solar masses per year when we're in this ULERG stage. So a little side note, something I did that was maybe slightly bad. In your first test, I gave you all a ULERG to calculate a star formation rate for, which I think confused some of you because it had just a really, really high star formation rate, which was correct. It was a ULERG. But that might have made things a little bit more tricky, and maybe I should have given you a more normal galaxy. So I apologize. But most of you got it, so we were okay. But that was why that one was so bright. I think it was ARP 229, which is you. And then over time, after we run out of, if we go through this huge burst of star formation, we use up all of our gas and dust, and we slowly decay into that red and dead elliptical after about 2 billion years after the actual merging process. The bottom graph here, I don't understand quite as well, but the idea is this is the luminosity of the central quasar divided by the stellar luminosity of the system, but divided by L star. So this is the luminosity of the quasar in solar luminosities. That's what it is. And what we can see is that the central quasar before the merger isn't super bright, but maybe as we start dumping some material because of just these dynamical interactions, we start to get a little bit of a brighter source in the center of this galaxy. And then just right after we have the spike in star formation happens here, and then right after that, there's a spike where the central quasar is the brightest thing in this galaxy for a brief period of time, but that fades really rapidly, and we end up with our elliptical without a quasar. I don't fully understand the spikiness. My guess is it's something to do with their model that has some stellar feedback in it, but I think that's a model thing that I don't fully, completely understand, simulation property that I don't fully understand. So just to show this, and then I'll pause. This is one of my favorite videos I've ever seen, but it compares kind of a simulation. This is an older simulation, but a simulation of a galaxies merging to actual images of galaxies merging. And just to show that we do our computer simulations, despite me being a persnickety observer who wants to actually see the stuff, our computer simulations are ridiculously incredible, and they provide just a phenomenal tool for understanding galaxy evolution. And they let you get a three-dimensional view, which we can never do as astronomers, as observational astronomers. We can't rotate our galaxy around and see it from behind. So, any questions on this kind of stage process of galaxy evolution? Okay, so our activity for today, on your assignments page, there's a thing called collisions that has just a link to a quiz. And it's going to just kind of walk through some questions where we can classify collisions and just think about what's happening in this collision, what might happen in the future for these two galaxies. And then just also thinking about some stuff, taking what I said and like thinking about where we might see different things, and looking also at the Hubble Ultra Deep Field and trying to put some of this together. So that's how we're going to wrap up today. I'm hoping there's a little time at the end where we can come back together and discuss things as a larger group, but we'll kind of see how things go. So I'm going to go ahead and open breakout rooms unless there's any other questions or issues with this. Rooms should be open. I'll be around to answer questions as you work through this. Two galaxy, and look, it's merging. So that's a good sign for what I was hoping you would find. It's just a fun thing to play with. And the Hubble deep fields are just very, very cool. But just to wrap up, my main idea for this was for you guys to get to first just think about classifying galaxy mergers, and how, since these two galaxies look like they're kind of two large-ish disks that are rotating in an orthogonal manner, they'll probably end up after, billions of years becoming a elliptical galaxy that eventually runs out of fuel. So that was kind of my thought for this part. And then as you go through, the other thing I wanted you to look at was just the Hubble Ultra Deep Field. Like I said, I think it's a really cool image. And see that when we look at the most distant sources, the really high redshift galaxies, so these are like Z of 4 to 6 or so, you see maybe 3 has a collision, maybe 2 has a collision, but most of them aren't colliding during this period. Besides that, it's really hard to tell anything about these galaxies besides the fact that they are red. They are red because they're high redshift, so all of their light has been shifted to the red. So that's cool. But when we look specifically at Z of 2, and we look at some of the really bright guys at Z of 2, we see that a lot of them have not only one collision occurring, but potentially multiple galaxies colliding. So why we see that peak in the cosmic star formation rate history at Z of 2 is probably very closely related to this large number of collisions happening in galaxies that are redshift 2. The one other thing I wanted you to kind of consider in this activity was why we might see so many more ellipticals in clusters of galaxies. And that's typically because you need collisions to get an elliptical, probably. So you're most likely to get collisions when there are a bunch of galaxies in the same place, therefore in clusters. So another hint that we do actually see ellipticals more in clusters, so another hint that they're probably forming from collisional processes. So with 1 minute to spare, did anyone have any other questions or thoughts as they worked through this?